Hello everyone, welcome to my channel Indian School of Physics. This is Nitin here, and today I have come up with a very different and very amazing problem. So it is Wheatstone bridge in AC circuits. It's a rare problem, but today we are going to discuss two different cases of it. So here is the statement of this problem. There is a network of a detector D and four unknown boxes with their reactance values as shown in the figure. The inside circuit components of each box is also described. The given network is connected to an AC source. Under what conditions the detector will not detect any current? And one note is given that such networks are called as Wheatstone bridge. So as you can see here, there is a Wheatstone bridge, and these are the four boxes which are given, and their reactance values are given as Z1, Z2, Z3 and Z4, and it is connected to an AC source. Alright, so we have to find the condition so that this detector is not going to detect any current. So it's like a balanced Wheatstone bridge, and in first case we are taking this type of circuit components. It can be any other combination also. Only thing will be calculation may become slightly tough. So you can see green box is a series combination of inductor and resistance. Red box is resistance capacitor. Blue box is just resistor, and yellow box is just inductor. Alright, so here there is a very special thing about this problem, that not all combinations will give you the condition for which current can be zero in the detector. That's the reason it makes it a very special problem. By the way, it's an original problem here. So I'm going to discuss this part first, and then we will see whether such type of combination can really give current zero in the detector or not. So let's discuss the concept part. If detector detects no current, then the bridge must be balanced, or you can say if bridge is balanced, I can simply write Z1 by Z2 is equal to Z3 by Z4. So that was the condition for DC circuits also, and here also it works. I'm not giving you the proof, but if you'll require, we can maybe in a separate video I can do the proof for this condition also. Do let me know in the comment section. So here this green box, you can say one inductor and one resistor. So I can write this Z1 value as R1 plus J omega L1, where J square is minus 1. Similarly, I can write for this R2 minus J by omega C, that is the value of Z2. Similarly, for blue and yellow box, I can write R3, that is Z3, and this will become omega L2, J omega L2, that is the value of Z4. So when I'm going to substitute this into the condition of balanced Wheatstone bridge, Z1 by Z2 is equal to Z3 by Z4. If I apply that, I'm going to get, just see here, what I am doing is Z1 by Z2 is equal to Z3 by Z4. This is the condition for balanced Wheatstone bridge. So when you do that, and now if you simplify, take this in this direction, and here you multiply like this and equate, you are going to get this equation. And I have written here, observe this equation. Observe this equation. So the prima facie, if you start solving just by comparing coefficients, you get a positive answer, something like this. A very nice answer will come, that is R1 R2 is equal to L1 by C. But I have written here that this cannot be the correct condition. So in order to find that, let's check why it is not possible. So if you observe this equation carefully, and left side there is one complex number, right side there is one complex number, and they are equal. So if they are equal, then their real part should be same and their complex part should be same. Now circuit components are positive, so you can see real part left side is negative and this real part right side is positive. Similarly, complex part here is positive, and here complex part is negative. So definitely such type of possibility cannot arise. This equation itself is not possible. That means our combination of this combination cannot create the detector current to be zero all the time. I hope you are able to understand this. So people make mistake here. They will one option I'll give as R1 R2 is equal to L1 by C, and people will mark it, but this will not be the right answer for this problem. So you need to be very, very careful. As I have written here, this equation is not practically possible. So if it is not practically possible, then let's find another set of circuit components for which we may get a meaningful answer. Note that here it's very important that not all combinations are going to give current zero. Only few specific combinations of circuits Z1, Z2, Z3, Z4 can give you current value to be zero. So now I'm slightly modifying this. I'm taking one resistor, one capacitor, then one capacitor, then one inductor, one resistor, and another resistor. So when I again apply Z1 by Z2 is equal to Z3 by Z4, so I am going to get R1 minus J by omega C1, and similarly here this is divided by minus J by omega C2. This will become R2 plus J omega L, and here it is going to be divided by R3. Now here and here, if you multiply these two, if you are multiplying these two and separate the real numbers and imaginary numbers, then you are going to get this R1 R3 is going to be L by C2, and from here I am going to get this R3 by C1 is equal to R2 by C2. You can see here the real part is positive, here also it is positive, complex part is negative, here also complex part is negative. So such type of possibility can lead you to one answer, and in that case this is going to be the correct condition. Whenever these conditions are satisfied, our detector is going to give zero current all the time. You can leave your answer here itself, though I have slightly further I have solved it, and I get this value as R1 R3 C2, that is equal to R1 R2 C1. This is going to be the final answer for this problem. I hope you have enjoyed this problem, and I'm pretty sure this will be a new problem for most of you, right? Even the idea will be probably new for most of the people. So if you have enjoyed this problem and it has given some learning, and if you have learned something from this video, please leave a like, share it with others, and if you haven't subscribed my channel, please subscribe it. I'll be coming up very soon with another amazing video. Thank you. Thanks for watching it.